In this section, we're going to talk about spent fuel isotopic characteristics. So we have the spent fuel. The question is, what is the spent fuel isotopic composition? So we begin with a fresh fuel assembly, and that fresh fuel assembly has some initial enrichment of U-235 if it's uranium fuel. So there's U-235 and U-238 in the fuel. And then it goes through some irradiation history while it's irradiated in the reactor. And then it is taken out of the reactor and has some subsequent cooling time associated with it. And then we get to the spent fuel. And in our spent fuel, we have the uranium, the U-235 and the U-238 that was there in the beginning. But we also have higher actinides and fission products that are now in the spent fuel. And as it turns out, the initial enrichment, irradiation history, and cooling time all factor in to that specific isotopic content of the specific spent fuel. The initial enrichment serves as a starting point for the fuel, and then the cooling time is simply radioactive decay after everything is produced. The radioactive isotopes that are in the spent fuel just decay, and so that's simple to account for. The major changes happen during the irradiation, the fission, and absorptions that occur. So let's take a look at the fuel changes that occur during irradiation. If it's uranium fuel, you start with U-235 and U-238, and you have a neutron absorption. Then, if it's in the U-235, you can have a fission, which produces fission products. However, you can also have non-fission reactions that produce higher actinides than both the U-235 and U-238. So let's take a closer look at that. Here we have a figure denoting the uranium buildup and decay chain for higher actinide production. The individual isotopes are represented as boxes in this figure. You have arrows between each of the isotopes with the type of reaction that's denoted or radioactive decay that leads to the following or subsequent isotope. The isotopes are also labeled with colors to denote the isotope half-life, and the half-life key is given in the upper left corner there of the figure. So beginning with the fresh fuel, you have only uranium, that's U-235 and U-238, and there's a little bit of U-234 in there too. And then let's look at uranium-238, and it absorbs a neutron. It then becomes U-239 through an N-gamma reaction, a neutron-gamma reaction, and then has a beta decay, goes to Neptunium-239, and then that has a beta decay that leads to Plutonium-239. And then the plutonium can have further absorptions and lead to higher isotopes of plutonium, or that can subsequently lead to americiums and curiums and other higher actinides. So if we take a look at the major actinide content, the depletion and buildup of uranium, both 235 and 238, and plutonium-239. So in this figure, we have burn up on the horizontal axis, and then on the left vertical axis we have the uranium content, and that's on a logarithmic scale. We also have the plutonium-239 content on the right vertical axis, and that's in a regular non-logarithmic scale. And as you can see, both uraniums decay. Not too much of the U-238 goes away. That remains relatively constant. The U-235 experiences a significant drop because that's where all your fissions are, and there was much less uranium-235 to begin with. And then your plutonium builds up as you go on. You can see that plutonium-239 curve starts to level off. If the burn-up went higher, it would actually kind of turn over and come back down as the plutonium becomes a major fission source within the fuel. Now let's take a look at an example of fission product buildup and decay. Here we have a decay chain leading to barium-135. And as you can see, if we look at barium-135 on the top there, it's produced directly in fission, but then it's also produced from beta decay of its parent isotopes. You can begin all the way down with the fission leading to tellurium-135 at the bottom right corner of the figure here. And that beta decays to iodine-135, to xenon-135, and to cesium-135. The xenon can also experience a neutron gamma reaction that leads to xenon-136. And in this figure, both the barium-135 and the xenon-136 are stable isotopes. The other are all radioactive. So the next question is then, how does irradiation history affect fission product buildup? So we're going to take a look at 5 different irradiation case histories and see how that affects the buildup of 2 separate fission products. We'll take a look at it in a second. So let's first go through the 5 cases of irradiation history. So in this first figure, we have 3 irradiation history cases. The first case was our original case when we began in the earlier sections. It has a specific power of 35 watts per gram and is irradiated for 1,000 days. You can see in this figure the days of irradiation are on the horizontal axis and the specific power is on the vertical axis. And then the second case uses specific power that's half the original case at 17.5 watts per gram and irradiates for double the amount of time, 2,000 days. And the third case irradiates at double the specific power for half the amount of time. And then on this next figure, we have case 4, which irradiates at 35 watts per gram, as in case 1, but also has 2 20-day shutdowns inserted during its irradiation history, so it winds up being a 3-cycle irradiation. The 5th case is actually a 4-cycle irradiation where the fuel assembly we're looking at actually only gets irradiated for 3 of the cycles, but the reactor operates on a 4-cycle pattern. So the specific power is 35 watts per gram, and the total amount of irradiation time is actually 1,000 days, but then we have 3 20-day shutdowns that are inserted, and for 1 irradiation cycle of the reactor, the spent fuel assembly is pulled out, so it doesn't get irradiated for 1 cycle, and it experiences effectively a longer shutdown time in that case. All right, so now that we have our 5 irradiation case histories, let's take a look at an example fission product. And for this example, we'll look at neodymium-144. And we can see its buildup diagram here, and it's just produced directly from fission. Now let's take a look at the figure that shows the concentration of neodymium-144 on the vertical axis as a function of fuel assembly burnup on the horizontal axis. And as we can see, all 5 cases just line up right on one on top of the other, and as neodymium-144 is produced. And so the production of neodymium-144 is only a function, only dependent on fuel assembly burnup. Doesn't depend on anything else because it's produced directly from fission, so it just correlates to the amount of fissions that occur in the fuel assembly, which is represented by burnup. So if we take a look at another fission product example, here samarium-147, we see from its fission buildup diagram that it's produced directly from fission, but it's also produced from the decay of another fission product, promethium-147. So if we look at our figure here showing the concentration of samarium-147 as a function of burnup, we see we have different profiles for the different case irradiation histories. And there are 2 things that are leading to the differences between the different cases here. The first is this N-gamma reaction that's dependent on the absorption rate and proportional to the specific power that the reactor or the fuel assembly is being operated at. So when the reactor is being operated at, or the fuel assembly is experiencing a higher specific power, then more of the promethium-147 is being absorbed and becomes promethium-148 than it is allowed to decay at a lower relative specific power case. So if we look at our figure here, we see case 1 is kind of right in the middle, this dark blue curve, and that'll be our baseline. But then when in case 2, there's a much lower specific power, you wind up with a much higher production. You see the case 2 curve, the pink one, is much higher than case 1. And for case 3, when the specific power is doubled during the irradiation history, we have a much lower production of samarium-147 because more of the promethium-147 is experiencing a neutron absorption because there's a greater population of neutrons as a result of the higher specific power. The next thing that makes a difference here is the half-life of promethium-147 is proportional. It's on the order of the cycle times or the shutdown time. So the half-life is about 2.6 years, and the cycle time is on the order of 300 days, about a year. So those are about the same. So you see, especially in case number 5, when the fuel assembly is out for an entire irradiation cycle, that is where the big buildup there is from the decay of promethium-147 to samarium-147.